Welcome to episode 3 of our Mastering AI ML series, How Machines Learn. We'll explore the 3 fundamental training paradigms, supervised, unsupervised, and reinforcement learning that power every AI system you use. This program is brought to you by the Series of Thoughts team. Every AI system has to learn, and the training approach varies by problem. The 3 methods are supervised learning, like a teacher grading homework, unsupervised learning, like exploring unknown terrain, and reinforcement learning, like a game player optimizing their score. The training approach is critical. Before building an ML system, ask, do I have labels? This single question determines the learning paradigm. Choosing the wrong one is a common and costly mistake in applied ML. By the end of this episode, you will be able to explain all 3 paradigms and identify which type fits a given problem. You'll also understand RLHF, LLMs, and the explosion of large language models enabled by self-supervised learning. Our roadmap covers supervised, unsupervised, and reinforcement learning, followed by self-supervised learning, and finally, how to choose the right approach for any ML problem. Chapter 1 focuses on supervised learning, the most widely used paradigm in production ML, which involves learning from labeled examples to make accurate predictions on new, unseen data. In supervised learning, the model studies input-output pairs, adjusting parameters until it can predict the correct output. It's like a student using an answer key to learn from mistakes and pass an exam with new data. The supervision comes from the labeled dataset, which is time-consuming to create at scale. The supervised learning loop is an iterative correction cycle called an epoch. It includes a forward pass, loss calculation, backpropagation, and weight updates. Hundreds or thousands of epochs sculpt a model that generalizes well beyond its training data. Supervised learning has 2 flavors: classification, where the output is a category, and regression, where the output is a number within a range. Both share the same training loop, differing in the output layer and the loss function used. Real-world examples of supervised learning include email spam filters, image classifiers, and house price prediction models. They learn from labeled examples to perform tasks with high accuracy. The catch with supervised learning is the expensive and time-consuming labeling bottleneck. Strategies to reduce cost include active learning, transfer learning, data augmentation, and weak supervision to auto-label at scale. Chapter 2 is on unsupervised learning. This paradigm involves just raw data, with no labels or right answers. The challenge is finding the hidden structure within the data. Unsupervised algorithms discover patterns and groupings without labels, much like an explorer mapping unmapped terrain. The algorithm defines its own notion of similar and different, making these methods both powerful and harder to evaluate. The 3 core unsupervised techniques are clustering, which groups similar data points, anomaly detection, which flags deviations from the norm, and dimensionality reduction, which compresses data for visualization and preprocessing. K-means clustering is an example of finding structure from chaos. It iteratively assigns points to cluster centers, measures distances, reassigns, and repositions centers until groups stabilize, creating meaningful data segments without human input. Unsupervised learning is essential for real-world applications like customer segmentation in e-commerce, fraud detection in banking, topic modeling and text analysis, and dimensionality reduction for data visualization and compression. Evaluating unsupervised models is challenging without labels. Evaluation relies on metrics like silhouette score for clustering, reconstruction error for autoencoders, domain expert review, and improved downstream task performance. Unsupervised learning excels when you have abundant unlabeled data and need to explore or compress it. Chapter 3 introduces reinforcement learning. Here, the machine is not told what to do, but given a definition of success and allowed to learn through trial, error, and reward. The reinforcement learning framework has 4 key components: the agent, the learner and decision maker, the environment, the world the agent acts in, the reward signal, a score returned after each action, and the policy, the agent's strategy to maximize cumulative reward. The RL training loop is a continuous cycle where the agent observes the state, takes an action, the environment returns a reward, and the agent updates its policy. The agent generates its own training data, leading to the discovery of superhuman strategies over thousands of episodes. The core dilemma in RL is the trade-off between exploration, trying new actions, and exploitation, sticking to known high-reward actions. The epsilon greedy strategy balances this by exploring randomly with a decreasing probability over time. Reinforcement learning drives innovations in robotics, like teaching robot arms manipulation tasks. It powers game AI, like AlphaGo, and optimizes real-time ad bidding and recommendation systems. Cart poll is the hello world of RL, where an agent learns to balance a pole by pushing a cart left or right. Through repeated trial and reward, the agent develops an optimal balancing policy without being explicitly told what balance means. Reinforcement learning from human feedback, or RLHF, is the advanced technique that fine-tuned language models like ChatGPT. It uses human preferences to train a reward model, which then optimizes the language model to align with human values. RLHF changed everything by making language models helpful, harmless, and honest, moving beyond mere next token prediction to alignment with human intent. This alignment is critical for modern conversational AI. Chapter 4 covers self-supervised learning, the secret behind the large language model revolution. This paradigm involves data labeling itself, removing the human labeling bottleneck. Self-supervised learning automatically generates supervision signals from raw data, such as using next token prediction in text. This allows models to scale training to trillions of tokens, forcing them to encode deep world knowledge. Self-supervised learning combines the scalability of unsupervised methods with the signal quality of supervised ones, enabling virtually unlimited data scale, making it the core training method for frontier language models today. Chapter 5 provides the framework for choosing the right machine learning approach. It helps simplify the complexity of selecting the correct training paradigm for your specific problem. The most fundamental question is, do you have labels? This single query is the initial pivot point that determines whether you pursue supervised, unsupervised, reinforcement, or self-supervised learning. Here is a quick look at the 4 paradigms. Supervised uses labeled data for classification and regression. Unsupervised finds hidden structure in unlabeled data. Reinforcement uses reward signals for long horizon strategy. And self-supervised generates labels from vast unlabeled data for pre-training foundation models. Applying this, detecting credit card fraud is unsupervised because fraud events are rare. Predicting loan defaults is supervised due to historical labeled outcomes. Training a robot uses reinforcement learning. And building a helpful chatbot requires self-supervised pre-training combined with RLHF. To recap key concepts, the loss function measures model error in supervised learning. The policy is an RL agent's learned strategy. The reward signal is RL's feedback mechanism defining success. And RLHF aligns LLMs with human behavior using reinforcement learning. In summary, you now understand the 4 learning paradigms and how to choose the right approach by asking if you have labels. You also know that RLHF is key to aligning powerful LLMs, which were unlocked by self-supervised learning at scale. In the next episode, we will show you real-world AI systems woven into your daily life. Before then, try identifying the learning paradigm behind 3 AI features you use today. You may be surprised by the answer.